The first thing I'm going to point out with this is just a diagram of the actual situation. Okay, so I have essentially the cart represented with a block on that diagram, and I have a normal force pushing perpendicular to the surface. We see the whole system is on an angle, and you see also a push force, but that push force is in the direction of the track. It's going downward like this because the direction of the push is along the direction of the track. Okay, now we're going to measure the angle of the track. I'm going to show you that when we start looking at the actual lab data, but that track angle actually mathematically is equivalent to basically this force that opposes our normal force. That's actually the force of gravity essentially in the y direction, this y component of our force of gravity. Okay, if we treat like this as our horizontal here, I'm going to show you that in a second. I'm going to basically turn the whole thing up on its side. But the idea is that this force in purple here is equal to that normal force, okay? Because we don't have, it's not falling through the track, it's not going to accelerate off the surface of the track, so that has to be balanced, okay? And then there is a component of this force of gravity that's pushing down the track, okay? And that is essentially our push force, okay? Now the neat thing is, mathematically, this angle between the line from the normal force, okay, and the push force, well, that is equal to the angle the track is on, okay? So you can see how I've kind of shown that, okay? Basically, I have a triangle here on the right, and in order for that triangle, the interior angles to sum to 180 degrees, which all triangles should, that angle here has to be 90 minus theta, and then this is another right triangle, so this angle here has to be theta. Okay, so that's important going forward, and I'll show you the next breakdown of the math in just a second.